Hello, I'm Ismail. Um, Today we'll talk about the introduction to about ARM processor, the basic of, and of course the basic of the microcontroller. Uh, Not programming, I think this is more on block diagram and system itself. Okay, first I will visit the microprocessor systems. So basically, microprocessor system is based on the just the what we have the input devices, then we have memory unit, and then we have output devices. And the middle ones, there, central processing units, uh, which is only the brain, right? Which is the brain of the processor. It has no, if related to or analog, we use the human being, man as the analogist. The central processing unit is only the brain without limbs, without hands, without legs, and so it just can think, but even cannot talk, uh, even cannot see, and so on. So to see or to talk, to do something, it requires input devices. For example, it requires keyboard, keypad, right? Whatever this, and then it also requires output devices such a latch, buzzer, whatsoever. And the central processing unit safe uh, actually just consists of the arithmetic logic units. By its name implies that it is used for the logic for arithmetics operations, and also for logics operations such jump, uh, conditions, conditional tests, and so on. Then it has a limited registers, and the registers is safe. It has two type of registers: the what we call as the specific purpose, such for indexing. For indexing, for example, it requires some let's say we call it as the program counter, right? Program counter. It has to hold the address of the start, then it's where start pointer. Then for multiplication, maybe for the example for the refer to 8086, it has the if I'm not mistaken, I forgot it. So, for counting, use CH or CL or CH register, and then for multiplication, normally use BL, BH, or BX registers. So that is a specific purpose register, and on top of it, it also has the multi-purpose register or general purpose register that can be used for anything, but limited. And then it has control units, right? Control units control the operations of the processor. So it has no memory basically, or it has we can see that it has no memory. So it requires the two type of the processor, the memory. Once the volatile RAM, right? RAM. So we can read data from, write and read data from, just like the notepad. The stack is with the our latch is our data is being kept temporarily read back for further processing and so on. Then it also need the area where we place the non-volatile data. Right? Now the data is normally is our program, right? So we need to play. It requires the what we call non-volatile memory. Previously, it is in ROM, read-only memory, but now it's in the flash memory. So we can have a look at the bus system or the processor. So all that components is connected to the CPU through the data bus, address bus, and control bus. So it has that these three data bus. So we can see that the address bus is used to pointing to the specific devices, either peripherals or random access memory or read-only memory, for example. And the controllers control the direction data, write or read operations, weights operation, and so on. That is generated by the control, handled by the control bus. And then the data bus is bidirectional. That means data can be, we can read data from read and random access memory, for example, and also we can write data to random access memory, but we only can read on data from read-only memory. Over there we can see that it's only one direction, and then the referral. We require all of these because of at a specific time, at any instant of time, only once locations can be accessed or for reading or for write by the processor, not all. Because of if it read, for example, from peripheral and random access memory at the same time, then the data will be contained, right? The data will be contained. I mean, there is the collection of data in the data bus, and there is a we call as data collection of that data. Then, I mean, we got the wrong data. So for this type of processor, so we allow only the data to be read or write at only once address or unique address being read or write at any instant of time, not all. So this microprocessor actually because it has a limitation in terms of once if you need to use a processor, then you need the read-only memory, you need the random access memory, you need the peripheral, the input. I mean, for example, if you need the parallel ports, right? Parallel ports for the parallel data in. Maybe you need the serial ports for the serial in data. You need the sometimes you need the max processor. You need the you need the interrupt controller, clock generator, and so on. So all of this makes the processor system, the microprocessor becomes bigger and bigger. So the cost is very expensive, make it become expensive and also difficult. All right. So then the engineer, right? The microprocessor engineer, right? Or designs the others that what we call a microcontroller system. So in the microcontroller, everything same. So we have central processing unit which already with arithmetic logic unit registers a lot of registers, right? A lot of registers. It has control time and timing unit, interrupt control unit, oscillator circuits, and and then it has also the read-only memory, random access memory, timers, counters, ADC, DACs, parallel I/O, serial I/O in one chip. So another advancement is a no more read-only memory being used because read-only memory require okay, read-only memory actually the first one is the one that we call as one-time, right? One-time programming, OTP. So normally it being programmed at the factory, right? So the program we give the program to the manufacturer, then it will be programmed for us, right? And later we have the reusable type of programmable PROM. However, we can program it, but remember it's only one time. We cannot erase it. Right? So when it comes to us, we program it. If you make a mistake, then throw it away. The second one that we have the EEPROM, EEPROM, single E, PROM. That means it can be erased and can be programmed number of times, maybe say 1,000 times, 1,000 times, and so we can erase it by expose the on top of the RAM of the ROM. We have the transparent window that we can see some sort of like a SK3 inside. So what we can do is open it, right, and then expose it to the ultraviolet sources, right. So normally it takes about 25 minutes to erase all the data inside it. Okay, so it takes time. So then comes another one that is we call as the EEPROM, right? Double E, erasable, electrically erasable, electrically erasable, programmable, read-only memory. So now we can erase it by using some sort of device that we call programmer. Just place it on the programmer, then we can select the ROM or the device that we use, and then we can delete it. Then we can write the code into the program. But whatever it is, it still takes time and so on. So now we have what we call as flash. And flash is some sort like normally it's working on SPI, serial paper interface. Means communications. It means we can write the data directly inside it very fast. That's why it's named flash. So simple. The same things we need to do. We can erase the flash either by block or by I forgot it. We can erase all them together, maybe all the data inside, and then we can write by block. We cannot write the data by byte. Compared to the EEPROM. EEPROM we can write data by byte, not by but flash must be in at least in block. So now the processor come with the flash, cheaper, much more cheaper, easier, right? So it become a bit popular. That's why microcontrollers started to be popular sometime in 90s. All right. What is ARM processor? So ARM processor is from within. It is advanced RISC machines. What is RISC machine? RISC machine is reduced instruction set computer. Right? So the philosophy is it has the similar length of the instruction sets. So the decoder, right, the decoder to decode the instruction is much more simpler because it has the same length, and then it's also designed to be more suitable for the compiler rather than to the human being. Right? Actually, the assembly language, for 8086, for example, or for say 8000, for 8051, all of them are designed based on SIS or complicated instruction sets, right? Computer. So the one advantage of them is the reach of the what instruction sets, right? So it's easier for us human being to understand to do the programming, the program using the assembly language rather than the RISC machines. Right? But however, the RISC machine is more suitable for the compiler. So there are, of course, there are a lot of compiler that support the RISC machines. We have, for example, IAR. We have a lot of the compiler, by the way. All right. So I'm actually just the middle of the IC. So if you see here, right, the core is only all others, right? All others, if you bought the microcontroller, STM32, for example, the IO, the peripherals, the timer, and so on, they're all developed by STM, ST by ST microelectronic, not by ARM. ARM only in the core. So this is the one that STM or other manufacturer bought from ST or from ARM, and then all the others doing by the manufacturer, for example, ST. So here I say algorithm for advanced RISC machines, ARM processor holding develops the instruction set and architecture of ARM-based product. And there are many silicon manufacturers that develop, produce, and sell microcontroller based on ARM architecture and core. For example, ST Microelectronics, and it is the only manufacturer selling a complete portfolio of Cortex M-based processor. ARM-based products have become extremely popular, and it is reported that in 2014 there are more than 50 billion ARM processors produced, and then it's equipped about 75% of the world's mobile devices. For example, Apple's iPhone are based on the ARM architecture. ARM version 8, that's it. Okay, so basically we have three types of Cortex. Right? The first ones, we have Cortex A, which stands for the applications. Right, this is the solution for the complex computing tasks, right? Such as the operating system, platform, Linux, and its derivative Android are the most common one. Right? This is the applications of this Cortex A. Cortex A equip the processor found in most mobile devices like a phone and tablets. Right? So now Cortex A are being used for the laptop and PC. I never use it. Actually, because it's not the second one that we have, Cortex M, which stand for embedded, right? This is the cheapest. We can say the cheapest. It is energy efficient and easy to use processor design for the low cost embedded market. The Cortex M family is optimized for cost and power sensitive and suitable for applications such as Internet of Things, creativity, motor control, smart metering, human interface, and so on. And most suitable for E&E, but suitable for E&E, electrical and electronic, engineering, suitable for micro, what we call another one, the robotic microelectronic, no, not microelectronic, what we call the I forgot it. And then in market segment, if we can have silicon manufacturer produce Cortex M, ST microcontroller is one of them. There are a lot of manufacturer that produce Cortex M, but the hero is ST Microelectronic. And then the last one that we have, Cortex R, stand for the real time. And this is actually the time for reliability, high availability, reliability, high availability, fault tolerance, maintainability, and deterministic real-time response are essential. So this is being used for real time processing. Okay, and I can say that this is the one that being used by the rockets, right, in system such that rockets, missiles, and drone, because we need the real time issue, car issue, motor issue, cycle issue. So we use Cortex R. There's some motivation to study the ARM processor. First, it is standard in the embedded world. Second, a pre-ARM based tool change. So it's possible to work with completely free tool change. Just by the, for example, just by the Nucleo board. That costs you around 70 ringgit, Malaysia ringgit. And cable, USB cable about 6 ringgit, or total up to 100 ringgit, right? Then you can experiment with it. And then quite an extensive portfolio. So as it has a quite extensive portfolio, if you study once of the context and processor, then you can use that knowledge or reuse that knowledge for the others what's context and processor too. Pin-to-pin compatibility. So most STM32 MCU are designed to be pin-to-pin compatible. 5-watt tolerance. And most STM32 pins are 5-watt tolerance. Remember, the processor is working at 3.3 volt, right? Then, so you cannot push it to 5 volt, right? So you need some sort like converter to convert from low voltage, you can say low voltage CTL, to the high voltage CTL, and to the TTL at 5 volts, right? And to drive something that at TTL, for example, right? And then when you read data from TTL, for example, then you need to drop that voltage to the low power TTL or 3.3 volt. So, but with the STM32 has designed some of their pins that compatible or 5 volt tolerance. And finally, it's very cheap. 32 cents for 32 bits. These are words I got from books. 32 cents for 32 bits. But some disadvantages of study the ARM. I see the learning curve can be quite steep for an experienced user, especially when the ST documentation has not been the best for inexperienced people to beg you and without clear example. Okay, this is what I faced. I realized that lack of SIL2 ST does not provide a decent formal development environment. And just previously, okay, for example, STM32Cube IDE was launched in 2019. When I start studying it, I still using the Kyle compiler. Kyle compiler just have the STMQMX, the graphical the graphical code generator for set up the basic code. So all that then we feed it to the Kyle compiler, and then we write the code from that or using that Kyle IDE. Fragmented and dispersive document. This is really true when you working with the bare metal programming. Bare metal programming. For example, if you need to know about, say, about the timer, you read from datasets A. Sometimes not all the information about it you can get from that dataset. You need to read another dataset. So it has a few, maybe 3 or 2 dataset that supports one's applications. So this is very difficult. And then bagi HAL, HAL contains some bugs and you know. Sometimes it cause confusions, right? Previously, when I use HAL STM Cube IDE, I got a problem to key in the device, but the latest, I just update it, then I got the ones that I can type directly the type or name of the device. And I don't want to talk about the functional block of the block diagram. The functional block diagram of the Cortex M0, is too much for us actually. So actually, but I just talk a bit about it. The CM0 core or Cortex M0 core has a Harvard architecture, meaning that it uses split interface to fetch instructions and data. Okay, so it has program data and it has program memory and then data memory. Okay, so it's not put all everything in one memory. So it looks like it has two memory, right? Two memory, one program data, that program memory. The other one is data memory. So it picks the instructions, right? And the data or the program and the data by it look like using two separate interface or separate hand, get the data from. So it must move faster. The interface between the Cortex M0 and manufacturer specific hardware is through three memory buses. So it use I code, right? So I code look like instruction code, D code, data code, and system, which are defined. System look like the control, right? Which are defined to access different region of memory. So you can see it here, right, in the figure. Then Cortex bus connects the D code I code bus to the Cortex M0 core to the bus matrix. So we have bus matrix here, right? This bus is used by the core to pitch instructions, get data, and access the AHV. All right, AHV. What is AHV? AHV stands for AMBA High Performance Bus, or APB, Advanced Peripheral Bus Resources. And then it has DMA bus. Right? So the processor come also with the DMA, right? DMA Direct Memory Access, Direct Memory Access. So DMA bus connect the HV master interface of the DMA to the bus matrix, which manage the access of the different master for flash memory and data from this SRAM, AHV, APB peripherals. So actually, in this type of the processor, Cortex M, it looks like we have two controller. One's from Cortex M0, the other one is from DMA. DMA. So DMA just not do this processing, just do the some sort like, okay, if I want to transmit data, okay, I can pass the data to the DMA to pass it, to transmit it. So Cortex M0 will not do that. So the Cortex M0 pass that task to DMA, so DMA will do that. To read data from DMA, from external also, we can pass it to the DMA. So once it's read, data is completed, then the data can be accessed by the Cortex M0. From where? From the memory. Right? Everything said through the memory is that we call direct memory access. Okay, so the data to be handled by DMA will be retrieved by DMA from the memory, and then the memory that the data that DMA want to pass to the Cortex M0, so will be pushed into the memory. So that is the use of the direct memory access. The bus matrix is composed of two masters, CPU, DMA, and three slave, NVM interface, SRAM, HB, APB1, APB2 bridges. And APB1, APB2 operates at a maximum frequency of 32 MHz. Remember, this referring to STM32 LOXX, right? So this is the block diagram. You can see the block diagram of the STM32, for example, here. So this block diagram is very important, right? Very important when we're going to use, for example, timer, like timer, for example, because timer 2 here, you see timer 2 here, it is connected to FPV1, right? So we need to know the clock for that we set for FPV1, right? To calculate the time elapsed for the timer 2. But when we use timer 21, for example, we need to know the clock of the FPV2, because timer 22, 21, and 22, for example, here connected to FPV2 and not to FPV1. That is the most important thing that we not understand. Others, no, just forget it, right? In the STM32, the I code bus connect the CM Cortex M0 instructions interface to flash memory. So remember, last time I said flash memory, where we place the program, right? The decode bus connect to flash memory for data page, and also we have a flash memory here for data, right? And the system bus. So flash memory, the data, right? The data and the program or instructions, both are placed in flash memory, but at the different, we can see at the different, what we call different maps, different area, right? Different area. And the system bus provide read and write access to RAM, read and write access to, see, this control, right? Control, just like the previous processor. This one we call control, and the STM32 peripherals. Okay, so this is the memory map, my memory map for the processor. Here you can see that flash memory here, flash memory, flash system memory, or SRAM, depending on the configuration. This is SRAM, right? Static RAM. You choose static RAM, not the what we call dynamic RAM. Then we have flash memory here from 0x 800,000, right? So we have FPV1 here. So FPV1, the address. So for example, here before FPV1, we have the USAT2. So USAT2 will be connected to FPV1, right? Yeah. And then we have iPod, yeah. IO port, right? IO port. So in here, IO port, I think here somewhere. This one, right? IO port. The address is that one. This is the address for them. Okay. And then to bridge the microcontroller to the physical world, right? The physical world, we have general purpose input outputs. Each GPIO pin can be configured through software as an output, either push-pull or pull-drain mode. Input, we have signal pull-up and pull-down resistor, or set to prepare alternate functions. Sometimes the pin can be used as input, as output. Peripheral alternate function means, for example, for transmitting data line, transmit lines or receive lines for you want. Input to the timer, input clock to the timer, and so on. Many GPIO many GPIO pins are multiplexed with digital or analog alternate function and can be remapped. Remapped individually using dedicated alternate functions register, right? Alternate function register. But because we are not using the bare metal, we use HAL. No need for us to know it in detail, right? In detail. All GPIO are capable of handling high current. The output speed for each GPIO can be configured to 40 MHz, 10 MHz, 2 MHz, and 400 kHz. But remember, we are using the STM F401RE, so please check what is the output speed for that of the STM32 for F401 GPIO. Check it by yourself. Okay, so this is the general purpose input-output GPIO block diagram. So in the FGC here, we have the protection diode, right? Protection diode. If the voltage more than VDD, we'll suppress it. If less than BSS, also will be suppress it by the protection diode here. So the data we can input the data here, go to the input register, right? And then we can what? We can write the data here to output data register, to output control, to control the push-pull here, open range here to the output, right? We can read the status. We can read the status of the output by reading the output data register here, right? Then we have the alternate functions for outputs, and then alternate function for the inputs here, and then for the analog input. For the input here, we have the pull-up resistor here, and the pull-down resistor, so we can switch this on and off. And it depends on the applications. Later, we talk about it in detail. Okay, input mode, the pin reads signal, example from button sensor. Mode spotting inputs, high impedance, no pull-up or pull-up. Pull-up inputs a weak resistor connected to BCC, logic high by default. For pull-down, a weak resistor connected to ground, logic low by default. Okay, so that's the input mode. This is the input mode, right? So we can push data here, pull up, pull down through the TTL submit trigger to reduce noise. Actually, by the submit trigger, we can have some sort of what we call hysteresis that we reduce the some sort of like bouncing of the signal, right? Then feed to we can read data from the input data register. And output mode, the pin sends signal to control devices, example light or relay. And then we can have two modes, push-pull, can actively drive both high and low signal. Open range output can only pull the low but require an external pull-up resistor for high signal. This is I will talk about in detail. So now for the output, I can push data here, right? So push-pull, push from PMOS and pull from NMOS, or we can have the open range. Open range, that means this one open, right? This one open. Alternate function, the pin is used for peripherals function like UART, I2C, SPI, PWM, etc. Each pin can support several alternate function, F0, F1, alternate function 1, alternate function 2, etc. But forget it because we're not using it we're not interested with it when we are using the HAL programming. Okay, so this is alternate function, for example. Analog, the pin is an analog input or output useful for ADC analog port to digital converter or DAC, digital to analog converter. If I know second, in STM32F401, we don't have DAC. We don't have DAC. For the STM32L053, we have DAC. Okay, so analog input. Then we have I don't think that we have analog output, so you can see. Yeah, we don't have it. Yeah, we don't have it. Yeah, we don't have it. Yeah, I forgot to copy the block diagram, right? The circuit. All right, and this is okay. Basically, we can arrange the push buttons such like this, where we have the pull up resistor, pull to BCC. So by default, this is active low because it is open. When we press, become low, so we call it active low. And when we have the external output pull up resistor, no need for us to set the internal. But if we don't have it, we can use the internal pull-up resistor, right? You can pull it up. So if you see the push button connected directly to the pin, and the other pin is connected to ground, that is the active flow push button, right? Active flow push button, and the internal resistor must be pulled up, right, towards. The other one that we have is, we have the resistor that we pull to ground, and you see another pins of the buttons connected to VCC, right? VCC. So if you see the button connected to VCC and the other one straight to the pins, so the internal must be pulled down. Sorry, this one should be pulled down. This one, pull down, not required pull down, not pull down, pull up. Okay, another things that we have is the if the microprocessor is used to drive the device, for example, LEDs here, active flow LEDs here, that require close or low and open, then we can use the open drain mode. So for connection that require only ground or logic 0, example of driving on off motor, for example, motor, for another example. The other one that we have is, sometimes we connect the processor to the IC. So of course IC require clear logic 0 and 1. So for that we need the push and pull. Push 1, pull 0. And now I will show you some of the, because of the process, the process is very small. If you can see, this is a modern processor, not PDIP. Not the one that with pins that you can connect it to the breadboard for experimental. Right? So the manufacturer produce the board. We have Nucleo 32, we have Nucleo 64, we have Nucleo 128. 64 is actually the pin number, number of pins. 32 also the pin number. So here I show you the Nucleo 64. So what you can see, it has two parts, the top and bottom. The top part is actually the debugger, downloader and debugger. And also here we have the converter for RS232 from low power TTL to RS232. So we can connect this one direct to the PC, right? So we can connect direct to the PC, the UARTs or UARTs for the application of serial communication. And also we can use this to download the executable file into the processor. So the bottom one here we have the processor. This is a processor, right? This is processor. Then this is the voltage, right? The voltage. Actually we can select either USB from USB, the power from USB, or the power from external. So external can be from 5 volt, or sorry, this one external 5 volt and ground, or from up to, if I know second, 18 volt, V in and ground, up to 18 volt, right? V in and ground. So at that time this must be connected to E5 volt, to E5 volt. And this one, the pin, the jumper, the jumper, you move it to right if you use power from USB. If you use external, either E5 volt or V in, then you need to put the jumper on the left. And this is the jumper for to power the processor. If you connect it, then you cannot download. You cannot download because the debugger cannot read your processor. Yes, pin assignments, right? Pin assignments very important, right? Very important. So the blue color is for Morpho, and the purple for Arduino. What is Morpho? Morpho actually is the application board, board or the target board that developed by the STM32 is safe. And Arduino is the target box that or application board that developed by Arduino Society, right? So this is the connections. You can read all this from the data sheet. And this is a diagram. From here we can see that actually here we have blue button and black button, and then we have LED. This one, LED. Okay, green LED. So we have green LED and blue button for user. So this is the this is a blue button. This is active low, right? It comes with the filter here. So we have filter, noise filter here, RNC for the bounce. Then if you see here, we have PA2 and PA3 that connected to the USAT, right? USAT. So USAT. So later we will use USAT2 for communication to the processor. And then here we have the LED. And the LED is connected to an active high and connected. You see this dot and jumper, SB42, right? So it's connected to PA5, right? So the green LED is connected to to PA5, and we also has here. No, this is the blue button, This is the blue button. This is the blue button too. Okay, this is the reset. You can see here, we have the reset, black button. That will reset your processor. Okay? It will connect it here and reset. So it goes here to and reset here. I can see. So this black button reset the programmer and also reset the processor. Okay, reset the processor. Another this is an example of the Arduino multi-learning seal that I use extensively in the class. So it has 3 time active low push button, 4 time active low LEDs, 1 active buzzer, 1 on board presets 0 to 5 volt. This one. So be careful when you are working with it. This one preset. Then 1 time 4 multi 7 this one common anode, and then 4 time 4 servo DC motor terminal, terminal, this one 1 time 4 times servo motor terminal, 1 time 4, 1 time 4, 1 2 3 4, 1 2 3 4, then 2 time external analog input LM35, this one. Okay, we can use for the LM35 or whatever, right? This one is 18B20. So actually this one is VCC and the other one is ground. The middle is for signal or data. This is a connection, circuit diagram. You can see it later on. This is another popular board that we use for the to program the processor, to study the ARM processor. This is Bluepill STM32F103C836. This is actually produced by the group of Arduino Society, right? This is not from the STM microelectronic, not from ST microelectronic. The connections, right? So that's all for this. If you want to know, come to Nucleo BMI.